All right, so here's a few more things about cryptography. So we can move to cryptography that really works, AES, really strong cryptography. And the whole point of Python is that people have written libraries that do everything you want. So you have to install the library, PyAES, which I've already done. And then you can encrypt stuff using AES. So I can make AES1.py. All right. Now, this is a really simple rudimentary implementation of AES, so I have not included any padding or encoding of data. So everything has to be 16 bytes, 16 bytes for the key and 16 bytes for the message. You could, of course, include padding to deal with other links, but I haven't bothered with this. So this is going to import the library. Then it's going to set the mode of operation to electronic codebook, which is the simplest and least secure method, where it encrypts each block of 16 characters independently. And then you can encrypt it, and you print the output in hex, of course, because it's like XOR. When you encrypt stuff with AES, you get bytes that are random looking, and they may not be printable. So let's see if that works. Python 3 AES. All right, so that's what encrypted stuff looks like here. And let me just modify it again. Suppose I had longer plain text. I'm just going to copy this, and I'm going to put it in here twice. So now I got 32 letters of plain text, and encrypt it again. And it has to be 16 bytes. That's rude. All right, I thought it would automatically do it block at a time, but I guess you do. Anyway, the point is, if you were to encrypt the same block twice, you'd get exactly the same output in electronic codebook. That's why it's not recommended. However, that's how it works here. So then you've got a challenge or two with that stuff. And then you can, here's how, getting closer to how it's actually used. You use password key derivation to start from a password and turn it into an AES key, which you do by adding a salt and hashing it many times with some hash function. That's how it's typically done. And then you have a key. And then you can use a more secure mode like counter mode. Counter mode adds a number that just keeps counting up, or a number related to that, to every block of data, so that identical input blocks will not lead to identical output blocks. That's one of the much more secure modes. Counter and cipher block chaining are commonly more secure. So you can play a few games with AES and see how it goes. And then there's the row method. We're going back to hashes. If you want to find hash collisions, which are how you rate the quality of hash functions, one common property of hash functions, like you may remember about 3 years ago, Google found a SHA-1 collision. They made 2 PDF files that were different, but they had the same SHA-1 hash. And hash collisions always exist, but you try to make hash functions so strong that nobody can ever find those collisions. And if there are no collisions that anybody can find, then the hash serves its purpose as a file signature. If you download a file, calculate the hash. If the hash is right, you would like to say that that proves that the whole file is intact. But if there are collisions, it's not intact. And the row method is the common way you find collisions. If you think about it, if I took a file and I hashed it, and then I hashed the hash and hashed the hash and hashed the hash over and over, I'll be moving through various hashes here. But if there's eventually a duplicate, then if I keep hashing it long enough, it will come back again, and I'll just go around in a circle. This is the actual thing that happens when you're using hash functions. And this whole thing looks like the Greek letter rho. So this is the row technique to find hash collisions. And the point of it is you don't have to remember all the hashes to find one of these. And so you can do millions and millions of hash calculations and only store some of them in memory, like every 10th or 20th one. And sooner or later, even since you're going around a loop eventually, you will find a collision. Anyway, so it's good to do this. And so you can do it with MD5. And waiting for a real MD5 collision would take a long time. So here, we just keep the last 2 characters. So there's really a really short hash, only 8 bits long. And of course, that has a collision in a hurry. So if you just calculate hash of hash of hash and keep only the last 2 bytes, 2 characters in hex, which is 1 byte every time, then pretty soon you find a region that just loops around here. And you can try a few of those to see how hash collisions are found. And another thing is the Md5 algorithm is so bad it was never approved by the government for any use at all. SHA-1 became the standard, but since Google broke SHA-1, SHA-1 is being replaced by SHA-2. And some people are nervous that SHA-2 will have collisions or other failures, so there is SHA-3 after them. And then there's Argon2, is even the later one, later than those, supposed to be very, very good for password hashing. So you can import Argon2 and make those Argon2 hashes and see how they go. Somebody just wrote Argon2 CFFI. You just import that library and you can make these Argon hashes and play with them. So those are more things to do to see the joy of cryptography in Python, which gets very easy. So I'm going to save this one.